For today's class, we'll be looking into electromagnetic field. And from the name, something is obvious. We have electromagnetic. So we have two fields there. So you can write electromagnetic field represents a joint field. It's a joint field. So we can say electromagnetic field is a joint field that represents magnetic and electric field. Or you can simply say electromagnetic field represents the joint interaction between electric and magnetic field. Now recall, from our last class we did magnetic field and we said for a charge in a magnetic field it is going to experience a force F, and that force is given to be QVB sine theta. So we can call this one magnetic force. Then electric force during electric field, if you recall, we talked about electric field intensity. And what is electric field intensity? It is a force that acts per unit charge. From here, if we cross multiply, we get electric force to be electric field strength multiplied by what? The charge Q. So you can say electric force is what? QE. So for a body or a charge in an electromagnetic field, it is going to experience a mechanical force, which is a force that is produced by the joint interaction of magnetic and electric force. In that case, it's going to experience a double force. So we are going to have the first one, which is what? The electric force, and it's also going to experience this magnetic force. So from here we can say this electromagnetic force equals to Q is common into bracket E plus Q plus VB, because we've already factorized Q. Now, if the charge is perpendicular to the electromagnetic field, then it means the value of theta is going to be 90. And sine 90 is 1. So in this case, the electromagnetic force becomes Q into E plus VB. In this case, what we have between V and B is what? Is a dot product. So this is the condition if the angle is 90 when the charge is perpendicular to the field. Now let this vertical line represent magnetic field. So that's B field. This magnetic flux density, and this one represents electric field. So when current passes through electric field, so let's represent E field. So electric field and magnetic field, they are perpendicular in this case. So in this kind of field, there are kinds of waves that are produced, and those waves are called electromagnetic wave. So ranging from radio wave, infrared wave, visible light, ultraviolet, X-ray, and gamma ray. They are produced in an electromagnetic field, and they all have speed of light. They travel the same speed as light. Alright, so from here, magnetic field, electric field. So if we have a charge, and normally for a charge, they are usually contained in conductors. So suppose we have a conductor of length L, and this conductor is placed in an electromagnetic field. So when current flows through this conductor, flow of current actually means the flow of electrons. So this conductor will experience a certain force, and it will move in a certain direction. So if this conductor is placed in this field, how will it move? So to know the direction of what? Motion. For a current carrying conductor in a magnetic field, we have to apply what we call Fleming's right-hand rule. So suppose we use the vertical axis for magnetic field, the horizontal axis for electric field. So the third dimension is the z-axis, which can be outside this board or inside this board. So to place this conductor in this field, it's either you roll inside or outside. So it's either you rolls outside or inside the board. To know this, we have to apply what we call Fleming's left hand rule. So the question is, what is Fleming's left hand rule? So you can write, for Fleming's left hand rule, we are going to use our left hand. So for our left hand, we don't need these two are useless. Then let's ensure we arrange our hands so that they are all perpendicular. Meaning the angle between this is 90. The angle between these two also is 90, and this to this is also 90. So it states that if the thumb, the forefinger, and the middle finger, if the thumb, the forefinger, and the middle finger are held mutually perpendicular to each other, with the forefinger pointing towards the direction of field, meaning direction of magnetic field. In this case, it will point up. And the middle finger pointing towards the direction of current or the direction of electric field. As you can see, this is what? Magnetic field. This is what? Electric field. Then it says the thumb points towards the direction of motion. You know, this force is electromagnetic force. When this conductor experiences it, it will be a mechanical force. Then the body will move. A force causes the body to move. So where will the body move? In or out? In this case, it's going to what? Come out. So this is what? Field, current, and this is what? Motion. So it's going to roll out this way. And again, Fleming's left hand stated that if the thumb, the forefinger, and the middle finger are held mutually perpendicular to each other, with the thumb, with the forefinger pointing towards the direction of field, meaning from north to south, from south to north, north to south, and the middle finger pointing towards the direction of what? Current, electric field. Then the thumb points towards the direction of what? Motion. And this Fleming's left hand can be applied in what? In a case where we have electromagnetic forces experienced by a body. So let's take cases where a body experiences an electromagnetic force. So the first one we are going to take is force experienced by a current carrying conductor in a magnetic field. Now, this is an horseshoe magnet. Horseshoe magnet is like a bar magnet bent to form a U shape. So if this is north and this is south, then the direction of the field is up. Magnetic field is always from north towards south. So the direction of the field is up here. Similar to what we have here. Now suppose a conductor is placed inside the space. It's placed there. So the current can enter either this way or this way. So when the current enters, it either this thing rolls outside, meaning from here it rolls outside the board, or it rolls inside the board. When we place this one here. So let's draw a diagram there to represent a conductor. Okay, we place a conductor inside the field. Okay, let's suppose the current enters this way in the conductor. If you fix, let's say there's a wire here, they'll put a cell here. Let's suppose the negative terminal is here, the positive is here. The negative terminal, positive is here. Then we connect this to the conductor. So what happens is that the current will flow this way. And when it gets here, it enters along. So the current enters this way. This is I. Now let's apply Fleming's left hand rule to see what happens. Will this thing roll outside or will it roll inside? So Fleming's left hand rule. When the thumb, the forefinger, and the middle finger are held mutually perpendicular to each other, with the forefinger pointing towards the direction of field. Where is field? North to south. So this one will point towards to the south. And the middle finger pointing towards the direction of current. But the current is not going this way, it's coming this way. So we have to turn other way, this way. By turning this way, we can see the field is north to south up. The current enters this way. Then the thumb points inward. So in this case, this conductor will roll inside. So this is the direction of motion. So meaning if the field is up and the current is to the left, then the motion is going to be inside. Let's put it this way, inside, in. But like what we have here, if the current is up and the field is to the right, then the motion is outside. So this is field, current, motion. This one is field, magnetic field, current. When I put in there, it means electric field. No, then so let me just put I here. current motion. That is Fleming's left hand rule. So the first case is force experienced by a current carrying conductor. So if we have a conductor in a magnetic field carrying current, it will what? Experience a mechanical force. Let's take the second. But before that, most times this kind of question, they don't draw it in 3D, this 3D, in 3 dimensions. Most times they are drawn in 2D. For example, they can just draw 2 straight lines and call this one north and this one south. Let me just put this way. North and south. So in this case, obviously, the direction of field is down. North to south. So this direction of field. We can be told that a conductor is placed in this field. A conductor is placed in this field. Let's suppose this way. So that the current enters from the direction given. Let's suppose the current enters this way. So where is the direction of motion? So in this case, the direction of motion, we can use the Fleming's left hand rule. Same way. First, this field. The field is pointing down. Then this current. If this is field pointing down, as you can see, the current enters this way. So this one has to go this way. So field, current, the motion is outside. So this conductor will roll outside the board. If it's maybe it's OBJ, or we are given paper to write, so it will roll outside the paper. But if you swap the field, maybe the south up and north up, it will now go to the other direction. So in short, note this. They might not draw it this way. You can draw it in 3D, in 2D rather. In 2D, most times the motion is usually inside or outside. Now, if we now replace this conductor with a loop, let's suppose we have a straight line. This is a conductor, but this conductor is now bent to form a rectangular loop, and the space in the field won't happen. Or is made to what? Form a circular loop. So in these 2 cases, what will happen to the conductor? So this time around, I will draw 2D, not 3D for this case. So first one is force experienced by a current carrying conductor. Second one will be what? Force experienced by a current carrying loop. So this represents a magnet. So the north will like horseshoe magnet, but we are drawing 2D. So this is north, this is south. So the direction of field is down, north to south. Now, suppose we have a conductor this way. Suppose this represents a conductor and the current enters this way. If the current enters this way, current, and the field is down, field, where will be the direction of motion? Okay, Fleming's left hand rule. Current, field is down, current is to the left, the thumb points upward. It means this conductor will come outside the board. Now, let me draw another conductor here. And this time around, let the current flows this way. Now, remember this current. Current flows this way. The field is down. Current flows this way. As you can see, let me come here. This is current. So this is current and the field is down. My thumb is pointing inward. So what happens is, this particular one will enter inside the board. Sorry, this one will come out, this one will enter. So let's now join them together. This is what we call a loop. So because for current to enter, we have to have a source. External circuit. Suppose here we have electric cell. So the current flows from the negative to the positive. So this is how the current enters. Current comes out here, flows here. So when the current gets here, it goes inward for this first part. The current comes here. Then for this second part, it goes where? Note, at this point, the current is also flowing through the conductor, but the conductor is parallel to the magnetic field here. Magnetic field is down, this part is also down. When the conductor is parallel to magnetic field, then what happens? Theta is 0 and sin 0 is 0. In that case, no magnetic force is going to be experienced. So this point has no what effect. But here is perpendicular to the field. So this one here will go inward, this one will come outward. So for every circle, when current flows once, if this one is going inward, this one is going outward, it will turn. Another circle will keep turning, it keep turning. In that case, we are creating a torque. There will be a kind of rotation. So when we have a loop, one side will go in, the other side will go out, and when it continues that way, we have what called torque. There will be what kind of torque. So in this case, this is as though we are converting electrical energy towards mechanical energy. In this case, the body is rotating, and this is the base of every motor. Every motor. So here we have the force pushing this one out, F, and here the force is pushing it in. And if you recall, these two forces, they have the same magnitude. Why? They are in the same field, they are both parallel, same angle, the field strength is the same, the current is the same. So these two forces are equal. So anytime we have two equal forces, and they are two equal forces, they are parallel, and they act in opposite direction, those two forces are called torque, are called couples. And when those two forces cause the body to rotate, that turning effect of couple is called what? Torque. And in this case, we can show that the torque produced here is a product of the magnetic what? Field flux, the area bounded within the conductor or the loop, the number of turns, and the current passing through it. So meaning the more the current, the more the torque, the more the rotation. The more loop we have, the more rotation. In this case, we have a single what? Loop. We can have several turns. So the more loop we have, the stronger the torque, the wider it is, the more the torque, the more the field strength, the more the torque. So you should know this in case you ask a question. The torque produced in this case is, we can call it burning. And I said with this, we can produce what we call electric motor and also moving coil galvanometer. You know, we've done galvanometer in electric field. How do they function? It is through what we call what? Electromagnetic what? Force. Before we move to application, meaning before we explain electric motor and also moving coil galvanometer, let's briefly talk about parallel conductors. If we have two conductors carrying current, we've done that in magnetic field. When the conductor carries current, what happens? Magnetic field is around it according to clenched fist screw. Now, if you have two parallel conductors carrying current, we notice that sometimes the two conductors, they kind of force that tends to pull them together or push them apart, depending on the direction of current of the conductors. So let's talk about force experienced by parallel conductors carrying current. Now, consider these two conductors. Suppose for this one the current goes up, this also goes up. When current flows upward this way, applying clenched fist screw, you can use left hand, you have to use right hand for clenched fist screw. As you can see, what happens here? The coil goes this way. Say we go for this two, it goes this way. Now suppose this one carries current up and this carries current down. If current is up, we'll still have this same thing here. Why for this one, it's not go this way, it's go the other way. So if we draw the magnetic pattern of these two, this one, they carry current in same direction. For this, they carry current in opposite direction. At the end of the day, for these two, we notice that there will be like the force between them will be attractive. So there's attraction here, and here there will be repulsion. So meaning these two move close to each other, they will attract. Meaning their field add up. While for this one, they repel. Meaning the field around them cancel out, the effect cancel out. Or we can show the pattern. But in short, in summary, when we have two conductors carrying current in the same direction, there will be attractive force between them. And if they carry current in opposite direction, there will be a kind of what? Repulsive what? Force between them. Okay, the tip of the conductor, let's say this is the tip of this first one, and here we have this. Let's try to see what happened at the top here. at the top, let's try to draw the field pattern and see how it will be. If you notice vividly, this goes this way, this also goes this way. So if we have a field coming this way, by the time we reach here, this one wants to continue this way also. So what happens, they will add up and the cycle continues. When this one is coming here, for this arrow is also going in this direction. So as you can see, the flow aligns. Because the flow aligns, so we are going to have an attractive force in between them. So this is the field pattern between two conductors carrying current in the same field. It is as though one of them will go like North Pole, the other is what? South Pole, because it's leaving here and it's coming towards here. What happened in this case? Let's let these black dots here be this, and this one here be this. So at the top here, for this one it goes this way, while this one goes this way. As you can see, at this point where they are this common region, this is going this way, this is going this way. So what happens? The field will not intersect. So we are going to have repulsive force between them. Let's see how the pattern will go. As you can see, this is going like this is going like this, so they will not intersect. So at the end, we'll be having something like this. So for the first one, it flows this way. The second one flows this way. So the center here will be a neutral point. So they will not intersect. So what happens at the end of the day? This goes this way, this goes this way. For this one, this move like this move like this. In case you are shown or the diagram is drawn, you should be able to identify. Same direction in this case, attraction, opposite direction, repulsion. Okay, back to the application of mechanical force produced in an electromagnetic field. So the first one is electric motor. Let's do that. Application of electromagnetic force produced in an electromagnetic field. Please, this is not electromagnetic force, electromagnetic field. In short, the electric motor. So an electric motor has 5 essential parts. So the first one is the armature or the coil. So the armature, or we'll call it the coil. What actually happens here is we have a coil of wire wound on a soft iron core. Then we need a field magnet, a permanent magnet in this case. Then we need a split ring commutator. It's like a ring splitted into 2 halves. A ring splitted into 2 halves. So we call it split ring. Then we have carbon brushes, which is one that's supplying the current from the source to the commutator. So the split ring are attached to the commutator. So we call it the split ring commutator. Then we need power supply because here we want to convert electrical energy to mechanical energy. So in short, what are electric motor? Electric motor, they are devices that convert electrical energy to mechanical energy. Now let's draw a diagram to show how electric motor operates. So here we have a powerful magnetic field. Let's say this is the North Pole and this is the South Pole. So that's for the magnetic field. The next one is the coil, armature. So this is let's use a rectangular coil. So this is it. Then we have to attach the commutator. On each side we have the halves of the split ring. One here, one at the other end. So here we have the split ring, and on each side of the split ring we have carbon brushes. Split ring gone, carbon brushes gone. Then power supply. Okay, let's start the operation. Once we press this switch, the circuit completes, is closed. Then current flows from here, negative to positive terminal. So this is how current flows. Once we lock this one, once we close this switch, current flows. So this long one, this short one, so this negative. So this carbon brush here is negative, this one is what? Positive. So what happens? When the current gets here, it continues along the path. So initially, let's suppose this coil is horizontal. So the current enters this way, meaning the current goes inside. Then the field, north to south, is to the right. So this current, this field B, magnetic field. Now, where will be the direction of motion? Fleming's left hand rule. Let's do that. This current goes inside. You see, this time around, current goes inside, field goes this way, then the tongue faces down. So meaning this part, we express a force pushing it down. The current continues, but here when the current comes here, it's parallel to the field, it has no effect. Then when it comes back here, the current is now coming outside. So when the current was inside, the force was down. When the current is coming outside, the force will be up. So these are couples, and they will cause a torque. The torque can either be clockwise or anti-clockwise. But in this case, what happened? This one is coming down, this one is going up. So we have what? A clockwise motion. A clockwise motion. So we have a clockwise motion. So this will keep rotating. For every cycle, it keep rotating. Now we've generated what? A torque from electrical energy. Mechanical energy from electrical energy is what we call what? A motor. If we want to rotate anti-clockwise, so it's either we switch this north-south, but if it's already built, the north and south is fixed. So what I want to change in this case will be the terminals of the cell. So if you put the long one here, the short one here, the current flows this way. In that case, it will move what? Anti-clockwise. That is a simple electric motor. Although in this electric motor, we have three losses. The first one is work done against friction. Loss due to the work done against friction because they are moving parts there. For example, this carbon brush is in contact with the split ring, even though it's insulated. Then secondly, we have what we call eddy current loss. I will explain that very brief or very soon. Eddy current loss. And lastly, we have conductors here that current is flowing through. So definitely, due to the resistance of the conductor, it will be generated. So there will be loss due to what we call Joule's heat loss. That's I square RT, due to the R, resistance of the conductor. While all these loss can be reduced, we cannot totally stop them. Then the second one is moving coil galvanometer. So these are the essential parts, about 7. But note, the key principle is that it works based on the turning effect of current in a magnetic field. Turning effect of current in a magnetic field. Same thing as this. Turning effect of current. When current passed through, it started turning in this field. So turning effect of current in a magnetic field. And this moving coil galvanometer is one of the most important instruments in electric field. Why? Because it's from this galvanometer we get ammeter and what? Voltmeter we can convert. Although this one is built to detect little amount of current or PD, but we can actually convert it to ammeter or voltmeter by either connecting a shunt or multiplier to it, either in series or parallel. We've done that during electric field. And I said during that time that we are going to reference back to how a galvanometer is built. So, but look at this a pointer before we move on. So, in this moving coil galvanometer, we need a pointer or a mirror with scale. So, whenever we don't use, if you use ordinary pointer, we have a scale. If you use mirror as a pointer, it comes with a scale. Anytime we now use a mirror with scale, it becomes what? Mirror galvanometer. And we talk about that during light wave. That is under the application of reflection that we have what called mirror galvanometer. So it's an example of moving coil galvanometer where the pointer used there is what? Is a mirror with scale. Now note, this coil, we call it moving coil because it moves. It's a light rectangular coil of insulated wire, something like this. Then it is suspended between magnetic pole. But unlike using this kind of pole, we use what we call cylindrical pole. We are coming there, I will draw that. Then it carries current and rotates when current flows, like this one too, it rotates when current flows. The field magnet is different from this kind of magnet, we are going to show that also. Then we also need a soft iron core. This is placed inside the coil. So, and it strengthens and makes the magnetic field it makes the magnetic field radar. I'm coming to that. And it improves the sensitivity. So one of the major functions of this soft iron core in the coil is to improve sensitivity. Then we need the suspension fiber, or we call it the torsion wire. And this is a thin wire that holds the coil. It provides what we call a restoring force. It's not that provides the torque. Also conducts current into the coil. Then this pointer or a mirror scale is attached to the coil and it shows deflection on a calibrated scale. Meaning the more current that flows in, the more it's going to deflect. So then it's calibrated. So then we have the scale itself, that we calibrate. Then lastly, damping system. This damping system is usually to prevent what we call eddy current. I mentioned it here, I'll also explain it later. So eddy current loss. So the damping system is usually we call it the eddy current damping. It helps the pointer stop quickly without oscillating. The pointer will stop quickly without oscillating. So these are the function of the essential part. Let's now draw it for you to see how it actually works. As you can see, this magnet is a bit thicker and longer than this. So this can be north and south, similar to what we have there. Let us place the soft iron core in between. Then around this soft iron core, we can now have what? The coil. So if you have a single coil, you have something like this. Then you can have multiple on it. Then let's place the control spring up and down. Then the pointer. Connected to the armature. Then we have the scale here calibrated. So this is scale here calibrated. So this pointer moves when current flows. The more the current flows, the more it deflects. So these two represent the terminals. Similar to this terminal, one will be connected towards the negative, the other to the positive terminal. So working principle. Once current flows through, using this two as terminal, we can connect something here to external circuits. So where we want current to flow. So when current flows here, in this case it will be positive, this will be negative. So when current flows inside this setup through this, what happens? This armature will move, will rotate. When the current enters, one part will rotate up and the other will rotate down. So and that will control this spring to deflect. So if there is no current at all, this spring will rest at 0 point. The more the current, the more it deflects. The more the current, the more and it has its full scale deflection, or the maximum current can take to have the full scale deflection. And this is working principle of a moving coil galvanometer. Before we continue, note down the following point. For this galvanometer, it has what we call sensitivity. How sensitive it is. Sensitivity. A galvanometer is considered to be very sensitive. If for a little change in current, it deflects. A little amount of change in current, it deflects. And this depends on several factors. To increase the sensitivity of a galvanometer, first, the magnetic field must be strong, must be extremely strong. Secondly, the number of turns of the rectangular coil must be increased. As we have many turns there. Then the third point is the area of the coil must be increased. The area of the coil must be increased. Then lastly, the string should be made of thinner wire. This spring should be made with a thinner wire to enable them to twist more easily. Such weak springs gives only a small control couple. So, and because of that, galvanometer has many advantages. Sometimes we can, the sensitivity of a galvanometer, let me use a symbol for it. The sensitivity can be expressed as, the current you can measure per a slight per degree of rotation. The current, they can make it rotate per 1 degree. So it can either be amperes per degree or volts per degree. And all these points is gotten from where? Recall I told you the torque produced in a motor is Barney. So this will represent the field strength, electric field flux, magnetic field flux. This is the area, and this is number of turn, and this is the current. So in this case, for a particular current, for the torque to be very high, this three must be very high, and in addition to it, the spring must be very thin. Please write the following point. It's very important. It's very important because the question can come from it. Number one, advantage of moving coil galvanometer. It has many advantages. We have other forms of galvanometer which we are coming there on when we get to electromagnetic induction. So number one, it has a uniform scale in which equal division represents equal steps of current or PD. It has a uniform scale. Note that. And that uniform scale, it is as a result of the radial magnetic field. This radial magnetic field. That's why it has what? A uniform magnetic what? Uniform scale. 2, the high sensitivity enables very small current to be detected or measured, so meaning it has high sensitivity. Secondly, because of its strong magnetic field, no extra measures need to be taken, meaning we don't need what to shield away any effect. So meaning if you have any other magnetic field around it, it might not affect the galvanometer. Why? Because it has a very strong field. But at the minute it has, we need what? A magnetic what? Shield, which we explained in our last class. We are going to put it, we are going to put this galvanometer inside a ring of what? Soft iron core. So if you have any external field coming, it's not go directly into it. Suppose this galvanometer, they are going to what? Move, and it will not affect the galvanometer. But for this, it doesn't need it. Why? Because it has its own strong field. Then the third application, over other galvanometer is 1. This particular moving coil galvanometer can be converted to what? Ammeter and voltmeter. I've said that initially. If we connect it with necessary or the appropriate value of resistance, either in series or in parallel. To convert galvanometer to ammeter, we need a shunt in parallel. And to convert galvanometer to voltmeter, we need what? Multiplier in series. And we've already shown the formula for the shunt resistance and the multiplier resistance. If you've forgotten, you can go and check the notes. So this is for what? Multiplier resistance. And for shunt resistance, so if you recall, this is formula for shunt resistance. Is a resistor of a low resistance connected in what? In parallel to a galvanometer, so it can work as an ammeter to measure large current. And this multiplier what? Resistance. A multiplier is a resistor of high resistance connected in series with the galvanometer to enable it to measure a large amount of what? PD. So we've solved question on this. This is just like a revision. Now lastly, I was talking about eddy current, but you might not still understand eddy current until we deal with what we call electromagnetic induction, which is like the opposite of what we've been doing. What we have been doing is, the fact that movement can be generated, motion can be generated when current flows. Now the opposite is, can we generate current by moving a conductor in a magnetic field? That is what we call electromagnetic induction. If we understand electromagnetic induction, that's how we can understand eddy current very well. So the next thing is to talk about what? Electromagnetic induction, which is the next part of this topic.